Okay, so I hope everyone saw my announcement this afternoon, wherein I shared with you the set of potential homework exercises, which includes all the exercises that I assigned throughout the um, summer one session so far, including a couple exercises from chapter 11, which I guess I'll assign on Monday or Wednesday. Um, so this is by no means are you expected to write out solutions to all these exercises, but hopefully they'll help you in preparing for the final exam. Okay. So with that being said, how did the homework go? Yeah, so Keenan asked if we're going to get practice finals. Yes, I said that yesterday. I'll send out the practice finals after class on Monday or Tuesday. Okay, so you'll have roughly a week to work with them before the actual final exam. Okay. Okay. So how did the homework go last night? Are there any questions about all the homework last night, which was mainly just identifying freeze groups for given patterns? Essentially running through this flow chart to determine what the groups of symmetries were of a bunch of patterns. And then of course there were the standard true false questions, which you should be comfortable with in format. So any specific questions about any of those? Okay. If not, then we'll go straight into discussing the 17 wallpaper groups. So I think you'll remember on Monday, I made this kind of informal definition of the ornamental groups, right? There are three classes of ornamental groups. And they are the rosette groups, which are just CN and DN. The freeze groups, which we spent most of this week classifying, which we completed yesterday. And then finally, we mentioned, and the first mention of this was at the very beginning of the term, the wallpaper groups, which are the groups of symmetries which have, so a more formal definition than anything we've said yet so far. It's a group of symmetries whose subgroup of translations is generated by exactly two translations, right? So that is to say, remember the main condition for a freeze group was that the subgroup of translations was cyclic, i.e. had a single generator. Now we'll insist that we have exactly two generators in a wallpaper group. Okay, so, and again, I'll ruin the surprise right away by telling you, again, reiterating, that there are 17 wallpaper groups. Okay, so let's just get some basic definitions and terminology down. And then after we make these basic definitions, we're going to take a step back and see the geometric similarity of the wallpaper groups and the freeze groups. Okay. So firstly, what I just said in words, a wallpaper group, which we'll denote by script W, is a group of isometries whose subgroup of translations has form a group generated by T1, T2. Now, I didn't tell you the whole story. There are some extra restrictions on T1 and T2, where if, let's say, we write that T1 is the unique translation that takes A to B, and T2 is the unique translation that takes A to C, then A, B, and C are non-collinear. Okay, so first of all, this is a choice to write tau 1 and tau 2 starting at the same point A, right? Now remember, a translation is uniquely determined by its translation vector, right? So even though, say for example, tau is the unique translation that takes A to B, we could start at any other point, D, and determine if we move the translation vector to that point D, whatever point it ends at, we can rewrite this translation tau AB to tau D, tau of D, right? That is to say, since a translation is just defined by its vector, any points that are spaced apart by that vector can specify that same tau. Okay, so in other words, if I find some pair of points A and B such that tau 1 takes A to B, then I can write tau 2 starting at A such that the vector that defines tau 2 points to some other point C. Okay, and this is the condition on the subgroup of translations for a wallpaper group, that these points A, B, and C have to be non-collinear. Okay, and once we get into once we actually get into the classification, you'll see why this is important, that we insist that A, B, and C are non-collinear. Okay. So let's continue. Another definition. The translation lattice for W determined by point P, let's say, is the set of all images of P under all translations in W. Okay. So, for example, an example of a translation lattice is we can take this common base point A that we chose for our two translations that define the generators of the group of the subgroup of translations. So let me write that down. So, for example, all translations in W are of form just tau2 to the j, tau1 to the I, right? That's of course because it's immaterial which order I write these in, right? Because all translations commute with one another. I just pick this order arbitrarily just to match the book's notation, but it really doesn't matter if I wrote tau1 or tau2 first. Oh, and furthermore, that's why I can express them just as single powers. That's why I don't have T2 to the I, T2 to the J, T1 to the I, T2 to the K, T1 to the, it doesn't matter because I can commute all those translations so that all the tau1s get together and all the tau2s get together. Okay, so all translations are of this form. Then just a piece of notation, tau2j, tau1i of A, which just by the notation of what the definition of a wallpaper group is the common initial point that I've chosen for tau1 and tau2. And we'll just call this, just label this AI sub j, or I should say A sub ij. The set of all these points form a translation lattice for W. Okay, so now we've chosen this notation somewhat suggestively. Remember, when we were dealing with Fries groups, we specified some way to choose a point on the center line of the Fries group, right? This point A. And then we labeled all the translations of A. And remember, in a Fries group, all the translations are just powers of some single tau. We labeled all the translates of A to be A sub I, right? Depending on how many times we apply tau to A. Okay. Now, this term translation lattice has a very explicit geometric interpretation, which I'll draw a diagram for now. I just wanted to make sure you had time to digest this bottom line of text, right? Okay. So this notation we'll use fairly frequently. Okay. Okay, so here's a diagram of what's going on. Let's say we have some point A here, and we'll just say that we go to B, which is just by our notation from the definition. This is tau 1 of A, which using the ij notation, the A sub ij notation is A sub 1 comma 0, right? Okay, and just in a schematic fashion, right? It doesn't have to look exactly like this, but let's say here's my point C, which is tau 2 of A, which in the ij notation is A sub 0 comma 1. So you can kind of start to see how this becomes a lattice, right? So this point we'll call A1 comma 1, right? Because I do the translation tau 1 to get to B, and if I do tau 2 of B, I get up to A11, okay? And I continue in this fashion. Put that a little further back. So what do I get here? I get A 2 comma 0, A 3 comma 0, A 2 comma 1, A 3 comma 1. And of course, there's no restriction on I and j being positive, right? We can have negative powers of tau 1 and tau 2, right? So what do I get here? I get A 2 comma negative 1, A 3 comma negative 1. Okay, so when I say translation lattice, I mean quite literally a lattice in the plane, a set of points that form a pattern that has quadrilateral cells, is what we call each of these chambers. Okay, so let's make that slightly more precise here. So a unit cell for a wallpaper group W with respect to a point A is a quadrilateral region. Quadrilateral region having vertices sorry, A sub I comma j, A sub I comma j plus 1, A sub I plus 1 comma j, and finally A sub I plus 1 comma j plus 1. Okay, so a couple things to notice here. First of all, note the use of the word A here. That is to say, each one of these is a unit cell, right? It's not a unique thing. There are many unit cells. Okay. Note also that I put in this clause with respect to some point A, right? So that is to say, these translations, tau 1 and tau 2, can be moved around to have any particular base point you want. You just want them to have the same starting point. Okay? So in other words, if I draw the translation lattice in the plane, it depends on this point A that I pick. Now, it depends on. That basically means where it is in the plane. We'll eventually see that the shape, what type of quadrilateral a unit cell is not affected by the choice of A, right? And you can kind of see that immediately because it only depends on the angle between the vectors that define tau 1 and tau 2. Okay, so as long as you have them at the same initial point, you can move that pair of vectors anywhere in the plane and get a shifted version of the translation lattice, but that will not affect the type of quadrilateral that defines the unit cell. Okay. This is also why we see right away why it's important to make A, B, and C non-collinear, right? That's the only way we can get a quadrilateral is if we have a triangle and then essentially flip that triangle across the line through B and C. That's the geometric intuition behind what a unit cell is for a wallpaper group, right? Or a translation lattice, if you like. Okay. So that's part one. And a somewhat obvious piece of terminology, but still, since we're mathematicians, we have to be precise at all times, mainly. A translation lattice with rectangular unit cell is called rectangular. Right? So if a unit cell has this property of being a rectangle, then we just call the whole translation lattice rectangular. Likewise, translation lattice with a rhombus as unit cell is, I bet you can guess, called rhombic. Okay. So just one comment. When you compare the wallpaper groups to the frieze groups, there's this similar geometric interpretation for frieze groups, right? That is to say, what is a lattice in one dimension? Well, instead of being in the plane, we're on a line, right? And the fact that all these unit cells are the same, the analog of that in one dimension is that to make a one-dimensional lattice, you just choose a set of points that are equally spaced from each other on some line. right? And that's exactly what we did when we made this choice of point A that was on the center of some Fries group F. And then look at all the translates of A. Those are all, if we go sequentially, A1, A2, A3, A4, those are all evenly spaced apart. Okay. So, right. Oh, and I guess I should just say, when we say unit cell, of course, we mean, so for example, this entire shaded region, you could call a cell, but it's not the smallest possible cell defined by tau 1 and tau 2. That's what a unit cell is, right? It's the minimal cell. Okay. Same in Fries groups, right? AI is a translate of A for all I. But the minimum translate, the thing that defines the geometric content that defines the generator of the translations, is the distance from A0 to A1. That's the unit length. That's the analogy of the unit cell here. Okay. And obviously there's some intuitive niceness to this, right? Because now that we're dealing with two translations, we're dealing with a two-dimensional analog of this procedure of finding a set of points by which we can test isometries for what is contained in W and not. Okay, and that's exactly the strategy we're going to be executing. All right. So I just want to go through a couple results about the odd isometries that W can contain. If W is a wallpaper group, what can we say about the odd isometries? Okay, so again, this is going to be a very kind of systematic exploration of the possibilities of what happens when we allow this to be in our group W. What can we say about the other things it must contain? How can we reduce that to a least number of generators? That's the type of thing that we're going to be doing. Okay. Okay. Preliminary results about odd isometries in W. Okay, here's our first theorem. If sigma sub L, a reflection in the line L, is an element of W, then either L is parallel to the diagonal, or sorry, I should say a diagonal of a rhombic unit cell for W. A rhombic unit cell for W. Or the alternative is that L is parallel to a side of a rectangular unit cell. For W. Okay? So in other words, if we contain a reflection, then we know that we must either have a rhombic translation lattice or a rectangular translation lattice. That's kind of a nice geometric thing to say. So let's attempt to prove this. So firstly, let's take a point A on our line L that we have a reflection in. And let's let tau, the unique translation, taking A to P, be the shortest non-identity translation. Okay. So that is to say, I've just taken P to be the shortest non-identity translation in W. Right? In a certain regard, I'm not constructing P explicitly here. I'm just saying, okay, taking an arbitrary point A on line L, I can find a P such that tau sub A comma P has the smallest, the least magnitude translation vector in W. That is to say, this is the smallest translation that can be written tau 1 or tau 2 to the j times tau 1 to the I for some I and j. Okay. Then we have two cases. Case one. This is the simpler case. Let's assume that neither does the line defined through AP equal L, nor is the line through AP perpendicular to L. Okay, so that is to say, the line through A and P and the line L intersect at some point. Right? Then let's set Q equal to the image of P under the reflection through L, reflection in L. Sorry. Well, our same old conjugation trick shows the following, right? That sigma L, tau of sub A comma P, sigma L inverse is of course equal to tau sub sigma L of A comma sigma L of P. Okay. What is sigma L of A? What's sigma L of A? Yeah, it's A because remember, we chose A to be on L. And reflection in L fixes the points on L exactly. It fixes L pointwise. Okay, so we get tau sub A comma Q, just from me insisting that Q is the name of sigma sub L of P. Okay, so here's one thing we know, that the distance AP is equal to the distance AQ. Right? Because the points on the line L are the points equidistant from P and Q, just because Q is the image of P under reflection in L. Right? Think back to when we worked a lot with reflections, and we use that property quite often. Okay. So, yeah, I want to erase this and draw a picture. Okay, pictorially, here's what we have. We have our line L that we have a reflection in, and we've chosen A on L, and then we've found some point P such that this translation vector has the shortest length in W, and then we have our point Q, which is the reflection of P in L. Okay, and we know that these two lengths are the same. So that is to say, AP and Q are non-collinear. So, in other words, we can say the following, that the group of translations generated by tau sub A comma P and tau sub A comma Q is the subgroup of translations in W. And in fact, L contains a diagonal of a rhombic unit cell. Right? Here's some point. This would be what? tau of AP, tau of AQ of A. Here's my rhombic unit cell. Of course, this is not a very good rhombus. I should have put this further out. But we see that not only is L parallel to a diagonal of a rhombic unit cell, but in fact, it contains a diagonal of a rhombic unit cell for W, of course. Okay. So now, let's do the slightly more complicated case of where L is equal to that line A through P, or L is perpendicular to the line A through P. I'm sorry, the line through A and P. Case 2. The line AP is in fact equal to L, or the line AP is perpendicular to L. Okay. So let's first let A be perpendicular to the line AP at the point A. And also let's let M be the perpendicular bisector of the line segment AP. Let's also let N be the image of M under reflection in A. Okay, so at this point, let me just warn you, this is going to be one of those situations where I'm going to set up a lot of notation and make a lot of relationships between these things I'm defining or defining their notation for. And then I'm going to draw a diagram and it should become much clearer what's going on. Okay, so I'm just going to keep saying more things just till I get to the bottom of the board, and then we'll erase everything and draw a picture. Okay, so furthermore, let's suppose that tau sub A comma R is the shortest translation in W that is not in the subgroup generated by tau sub A comma P. Okay. So let me make a claim. Then there are three possibilities. Then R, this point that gives us the shortest translation in W that is not in this subgroup generated by one of the generators of the translations of W. then R is on M or is on N or is in between. Okay. This is kind of perhaps a kind of bizarre claim, but once we draw the picture, I think it will become much clearer. But before we do that, does anybody have any idea why this seems plausible? It's near impossible to tell without the picture. I'll give you a hint. It's related to this translation, tau sub A comma P. So now let me clear the board and draw the diagram that will help you see this. Okay. So, well, actually, I lied. Let me give you a quick, tiny piece of algebra, and then we'll draw the picture. Okay. So, these conditions on R must be the case, since otherwise, one of tau sub A comma P, either by itself or inverse, times tau sub A comma R would be shorter than tau sub A comma R. All right, so let's see this. Okay, so we start with our point A and this point P, and we look at the line AP, and then we had this line A through A and perpendicular to AP. And we set M to be the perpendicular bisector of the line segment AP. Right? And then, of course, we set N to be reflection, the image of the line M under reflection in A. Which, of course, must also be perpendicular. Now, my claim is that R has to be either on M, N, or in between somewhere. And that's because if I take R to be where this X is, well, let's look at what this product gives me. So first I do translation from A to R. That takes the point A to the point R. And then in this case, I want to do the translation from A to P inverse in this case, because I'm above the line M. So that will take me to some place slightly above the line A, right? So in other words, the composition of those two translations is this, which is shorter than this, okay? And it's the same argument, so therefore R can't be above the line M, okay? And similarly, what if I put R down here? Well, first I do the translation from A to R, and then I do the translation from A to P. This time I use not the inverse, but just the translation from A to P. And this puts me somewhere up here. And this translation is of less length than this translation, right? It's shorter. So this is not R. R has to be in this strip, or possibly on M or N. Does that seem clear? Yeah. So P and S, when I draw this vertical line or this vertical line, oh, you're right. So I drew this way too long, right? Sorry. This actually ends up like here, because I'm just traversing this distance, right? Because that's the vector that defines the translation from A to P, is just straight up and of this length. So basically, I'm just using vector addition when I compose translations, right? Of course, this one is going down because I used the inverse when I supposed R was above M, and this is going up. Okay. So does that seem clear? Yeah, I guess I should say I'm not just traveling the distance. I'm traveling the distance in the same direction as A points to P that I go from. The same direction I travel in when I go from A to P. I.e., if I assume that there are coordinate axes around here vertically in the plus y direction, right? Okay. So are we okay with this? I hope. Okay. So, in fact, if we consider both tau sub A comma R and tau sub A comma R inverse, then without loss of generality, we can assume that that R is on M or on A or in between. Okay, so what I'm saying here is at first glance, this argument for this product being shorter than AR tells us that we have to be in this wide strip between M and N. But then, if we notice that tau sub AR and tau sub AR inverse have the same length, then we can restrict ourselves to either one of these half strips, right? Because we know that one of these based at A points up above the line A, and the other one must point below the line A. So that's what I mean when I say without loss of generality. We could treat either of those cases, and just because, I don't know, maybe I like writing the letter M better, I'm going to choose this upper strip. R must be somewhere in this upper strip, including possibly on the lines M or A. Okay. So now let reflection in L be equal to, I'm sorry, reflection in L evaluated at R, we'll just call S. Okay. And first, assume that R, sorry, capital R, is between M and A. Okay. So then remember, I kind of tried to compress a lot into this case 2, right? Case 2 consists of two possibilities. Either the line L is equal to the line through A and P, or the line L is perpendicular to the line through A and P. So first, let's say what happens if L is equal to the line through A and P. Okay, what happens in this scenario? Then what do we have? Tau sub A comma S times tau sub A comma R is a translation shorter than tau sub A comma P. Okay, again, this is not easy to see without drawing it out. So I'm going to erase these non-possibilities for R and hopefully be able to reuse this diagram. Okay, just do a little touch up here. Okay, so our first assumption is that R is between M and A. Let's say we take R here, and then we're allowing the line through A and P to be L. Okay, so then in other words, I set S to be reflection in L of R. Right? So now what I'm saying is that the translation, first we do the translation from A to R, right? And then we look back at this translation. The translation from A to S has this vector, right? So we just translate that vector over here. Actually, this ends up being on the line L, right? So this is tau of A comma S times tau of A comma R of A, right? Which just gives us this translation in the same direction as the translation from A to P, and necessarily shorter. Okay? So what does this imply? This implies, oh wait, maybe, right, okay. In this case, when L is equal to the line through A and P, R must be on M or A, right? It can't lie in between, under the assumption that L is the line through A and P. Okay, now let's quickly address the other case. What if L is perpendicular to A and P? I'm sorry, the line through A and P. Well, let's just write that down. If instead L is perpendicular to the line through A and P, then just a quick algebraic trick gives us another translation that is shorter than tau sub A comma P. That is to say, if we consider the translation from S to A, i.e. the inverse of tau sub A comma S times tau sub A comma R, then this is a translation shorter than the translation from A to P. Okay? So that is to say, if we let instead, now let me modify my diagram again. We're no longer allowing the line through AP to be equal to L. But let's say we now let the line A be L, which is perpendicular to AP. So Jordan asks, why must R be on M or A in the previous case? In the diagram, it looks like it's between them, and it seems to work. So going back to everything that I said before if here, okay? So by composing translation from A to R with translation from A to S, I do this vector addition, and I land on the line through A and P. And my translation, this composite translation, tau sub A comma S times tau sub A comma R, results in a translation that is shorter than the translation from A to P. And remember, our base assumption before we even talked about case 1 or 2 was that the translation from A to P is the shortest in W period. And then we found this point R, which must be the shortest translation in W that is not in the cyclic subgroup generated by the translation from A to P. So by my assumption that there's a reflection in the group W, I was able to construct a new translation, tau sub A comma S, such that the product of tau sub A comma S with this translation, which was supposed to have the property that is the shortest, that's not a power of tau sub A comma P, I was able to construct a shorter translation that must be in W, which is a contradiction. Okay, so that's going back to contradict our initial assumption that the translation from A to P is the shortest in all of W. Okay, good. So, right. If I now assume, instead of saying that L is equal to the line through A and P, I assume that it is perpendicular then what happens when okay, this is no longer my S because I changed what L is, right? If I take the image of R under reflection in S, what do I get? I get this now, S equal to the sigma sub L of R. Okay, now what happens when I take this product of translations? I have the translation that takes S to A, right? And then the translation that takes A to R. Now, I think it's probably clearer. Yeah, so this is a little bit superfluous. Maybe instead, why don't I put, actually, and you know what, I drew this in reverse order. I'm sorry. Let's get rid of these arrows. Okay. So I want to first, let's take the point A. Let's evaluate this product at the point A, just to see where A goes. Okay. So I first take A to R, and then I add the vector from S to A, right? I add this vector here. And then the composite is again this vector. Okay, so this is not sigma, sorry. Tau sub S comma A times tau sub A comma R of A. And you can see that the length of this composite translation is again less than the translation from A to P, right? Just by taking this vector from S to A and putting its tail at the head of the vector from A to R, right? And then I get this translation. So again, this is the same type of contradiction, whether L is equal to the line through P or L is perpendicular to the line through A and P, we still must conclude that R is on M or A. Okay. So okay, let us see what happens now, assuming that R is on M or A. I think I'll try to leave this diagram and possibly refer to it some more. Okay. So let's start with what happens if R is on the line M. Okay. If R is on the line M, then we have the following. The group generated by tau sub A comma R and tau sub A comma S is in fact equal to the group generated by tau sub A comma R comma tau sub A comma P. And why is that? Well, let me just write this algebraically first, since we must have the relationship that tau sub A comma S times tau sub A comma R is equal to tau sub A comma P. That is to say, the product of these two generators gives me this. So I can replace this as a generator. Basically, I can recover tau sub A comma S just by multiplying on the right both sides of this equation, tau sub A comma R inverse. Okay. Right. So, as I said, let me try to reuse this diagram yet again. And let me just clean this up a little bit. So if we have R on the line M, well, yet again, there are two cases, right? We have to address, there's two subcases. We have to address the case where L is equal to the line through A and P, and L is perpendicular to the line through A and P. Okay. So let's just do one of these cases, and you can convince yourself of the other one. Okay. So so let's just let L be A again, be perpendicular to. That's the one case that we'll draw out together, and then for homework, maybe change back our notation, make this be L, and draw S and see what you get. Okay, but you'll find the same thing. Okay, so reflection in L here gives us S down here, right? Where we're allowing our L to stay equal to A. Huh? Okay, so then what do we have? So, right, again, I have, if I evaluate the translation that takes A to R on A, I go to R, and then if I take the translation that takes A to S of R, right, I just translate this vector here, and I get P, right? So I get the full translation A to P when I take that product. Okay. So this means my unit cell is this rhombus, right? Well, then we see that L is parallel to the line M, which contains the diagonal of this rhombic unit cell. Okay. So this implies that L is parallel to M, which contains a diagonal of a rhombic unit cell, or W, script W. Okay, that's the case when R lays, that's half of the cases where R lies on M. Now, of course, if I switched A to L here, right, I would just have S also on M. That would make S this other vertex of the rhombus. I guess I should mention, yeah, I think that's fine. Okay, so let me just record that explicitly. Homework. Draw the case where R is on M and L is equal to the line through A and P. Okay. So, how about the case where R is on A? Well, this one is actually a little bit easier. Okay, so if R is on the line A, on line A, then we have that translation taking A to P and translation taking A to R. Is the group of all translations W and no matter if L is equal to the line through A and P, or if L is perpendicular to the line through A and P. L is parallel to a side of a rectangular unit cell for W. Okay. So in this case, you just get some translation that is in a vector that's orthogonal to the vector for the translation from A to P. Okay, so therefore you get a rectangle for a unit cell. And in either case, if L is equal to the line through A and P, it's parallel to one of the vertical sides, or both the vertical sides. And if L is perpendicular to the line through A and P, it's parallel to the horizontal sides of the rectangular unit cell. Okay. So I hope that it was okay that we reuse this diagram so much. I hope that it was clear what was going on. So, right. Before we go, I would like to tell you one more theorem, and then we'll prove that on Monday. Okay. And then we will have essentially done all we need to do in terms of preliminary results about odd isometries contained in wallpaper groups. And then we can characterize what needs to be said about rotations, the even isometries that need to be classified. Of course, the other even isometries are translations, but just by the definition of wallpaper group, we know what the translations have to be, right? We just have to have two translations based at the same point, having three non-collinear points as subscripts, right? So that completely characterizes what happens in terms of translations. After we talk about glide reflections, then we'll have to talk about what happens with rotations in wallpaper groups. Okay, so let me just state the next theorem that we're going to prove. We obviously don't have enough time to do anything meaningful in terms of the proof, but I'll write it down nonetheless, just so you can mull it over, or at least hearing it more than once might help slightly to digest the material. Okay. So this will be our next theorem to be proved on Monday. If a wallpaper group W contains a glide reflection then W will have a translation minus which is rectangular or rhombus. Okay, so if we contain a glide reflection in a wallpaper group, then the translation lattice must be somewhat well behaved. Right? It has to be one of these nicer quadrilaterals that we'd like to work with more than most. Okay, so there you have it. And the proof is a little bit involved. So I think that's all we'll say for today. So for those of you who may have joined late, there was a question at the beginning about when the practice finals would be released. I think I'll just release them on Monday after class, right? Just so you can really concentrate on studying for exam 4 on Tuesday. And check the announcements. I sent out a list of not only the homework problems that I've assigned over this this course, but a list of many other homework problems that had been assigned in previous iterations of the course. So I by no means expect you to have written solutions to these, but they may well help you prepare for the final exam. Okay. So have a good weekend, and I look forward to being back in a legitimate classroom on Monday, and hope to see some of you then, maybe even in person. Okay. So enjoy your weekend.